Welcome back, students, to the another session on analog communication. That is on unit number 6, pulse analog modulation. So, in previous sessions, we have solved some examples on sampling theorem. Now, we need to proceed for the types of sampling. So, here there are three types of samplings are there. Basically, there are two types. One is ideal sampling, and another one is practical samplings. Okay. But this practical sampling is divided into two parts. That is, first one is a natural sampling and second one is a flat top sampling. So first one is a impulse or ideal sampling. Impulse height is sampling instant. This is known as ideal sampling process. And this natural sampling and flat top sampling, it is commonly known as practical sampling. Okay. Now we'll understand one by one what is meant by ideal sampling and what is meant by practical sampling. Now three different sampling methods are there. So basically I just discussed now. One is ideal and this practical. The practical is divided into two parts. This is natural and flat top. So this first one represent the ideal sampling, or we can say it's a impulse sampling. Okay, so this is just impulse one. So whatever amplitude of input signal that followed by the samples or impulse signal, this is known as the ideal sampling. The second one is known as the practical sampling. In this first one, that is natural sampling, means whatever the amplitude of your input signal that followed by the sampling process. So this is curve shape is nothing but the known as the natural sampling. And the third one is nothing but the flat top sampling. With respect to of amplitude of message signal, the sampled signal as a top is nothing but flat. It does not follow the amplitude of your input signal. Okay, so we just mark the amplitude and get flat for some duration. So this is known as flat top sampling. Okay, so these are the three types of sampling methods. One is ideal, then natural sampling, flat top sampling. Now impulse sampling, or also known as ideal sampling. This is the case of ideal sampling with a sequence of unit impulse functions. Okay, so here important thing is impulse function, or we can say it's a delta functions. Okay, so in this ideal sampling or impulse sampling, the delta function plays an important role. Okay, so validity of this sampling theorem using the frequency convolution property of Fourier transform. Okay, so validity of this sampling theorem, this can be done by using the frequency convolution property of Fourier transform. Now let's take the sampling of x of t. Let's assume an x of t of any signal can be viewed as a product of x of t with a periodic train of unit impulse function x delta of t. Okay, x delta of t equal to summation of n equal to minus infinity to plus infinity delta of t minus nts. This equation is somewhat familiar to you. Okay, so graphically this can be considered as like this is your any input message signal, that is x of t. This signal is multiplied with a train of unit impulse signals. This is the train of unit impulse signal. At 0, this is delta t, this is delta t minus 1 ts, this is delta t minus 2 ts, this is delta t minus 3 ts, this is delta t minus 4 ts. Combinedly, we can mathematically refer this train of impulse signal by using this x delta of t equal to summation of n equal to minus infinity to plus infinity delta of t minus nts. Okay, now this signal and these signals are multiplied together sample by sample. The resultant will get a sampled signal like this. Okay, sampled signal like this in time domain, because on x-axis time t is there. Okay, so this sample multiplied with this sample followed the amplitude of message signal. Similarly here is the maximum amplitude, so this delta function followed the amplitude of message signal. Here is the amplitude of all delta functions are 1, so this 1 multiplied by something is nothing but something. Okay, so this is the sampled signal, and this is referred by xs of t equal to x of t multiplied by this train of impulse signal x delta of t. Now similarly, this signal is converted into the Fourier transform by taking Fourier transform. So let us assume the Fourier transform of this x of t is like this: x of f mod x of f, this magnitude of this signal. This is 0 fm minus fm, means bandwidth of this signal is fm. Okay, now this train of unit impulse is a Fourier transform is like this. Okay, x delta of f equal to 1 upon ts summation of n equal to minus infinity plus infinity delta of f minus nfs, that is 0 first fs, then 2 fs, and so on. This is shifted version of unit impulse signals. Okay, now these two signals multiplied together, then we'll get this type of signals are there. That is, this is first basic 0 signal, first fs. Okay, then second fs, first fs, 2 fs, 3 fs, and so on. So this is the frequency domain sampled signal. This is frequency domain sampled signal. Now using shifting property of the impulse function, state that this is some mathematical understanding of this sampling signals are there. You can refer from book also, or you can understood by this way also. Here, the shifting property of impulse function, that we know already, that any signal x of t is multiplied by a shifted version of delta function, that is delta of t minus t0, then it will get x of t0, means amplitude of signal, value of that signal at particular time period, that is t0 into delta of t minus t0. This is the property of impulse function. Okay, using shifting property of sampled version of signal x of t is given below: xs of t into x of t into x delta of t, that equal to summation of n equal to minus infinity to plus infinity x of t into delta of t minus nts, which will get by using this above property. Here we can refer as x of nts into delta of t minus nts. Note that multiplication in time domain will result into convolution in frequency domain. So this is simple mathematics. If you understand the properties of delta function, if you do not understand, then you can go simply and refer the properties of all delta functions from signal sense system, then you can understand easily. We can transform this time domain product x of t into x delta of t to the frequency domain by convolution x of f into x delta of f. Means that convolution or time multiplication in time domain is nothing but the convolution in frequency domain as the property of Fourier transform. So here the train of impulse function in frequency domain, it is referred by x delta of f. Okay, that equal to 1 upon ts summation of n equal to minus in plus in delta of f minus nfs. Okay, so convolution with an impulse function simply shift the original function as follows. This is the another property of impulse function, that is instead of multiplication there will be a convolution, that is x of f is convolved with the shifted version of delta function delta of f minus f nfs. In that case the whole signal x of f shifted to the nfs, which is nothing but x of f minus nfs. Okay, by using this property we can solve the sample signal xs of f as like this: xs of f equal to x of f convolution with x delta of f, that equal to x of f convolution with 1 upon ts summation of n equal to minus infinity to plus infinity delta of f minus n fs. So by using above property, here we can refer as 1 upon ts summation of n equal to minus infinity to plus infinity x of f minus nfs, as this x of f is shifted to x of f minus nfs using this property. Okay, so this is the sampled signal in frequency domain under the ideal sampling. Now here there are three cases of frequency. First, here sampling rate is fs equal to 2fm. It's exactly equal to Nyquist rate. Fs equal to twice of fm. Fm is the maximum frequency of your message signal. The separation between the spectral replicates is fs, and the figure is shown as like this. Means there is no separation between two consecutive signals. Okay, this exactly touch to touch signals are there, and this is possible in the case of fs equal to 2fm, and this is known as ideal case. This is known as the ideal case. Okay, so 0 fm minus fm. Okay, this is 0, then 1 fs, then 2 fs. There is no separation, there is no gap between two sampled signals. Okay, analog waveform can theoretically be completely recovered from the samples by the use of filtering. Now in second case, fs greater than 2fm, fs greater than 2fm, in that case the sampling frequency is very much greater than the twice of your input message frequency. That replication will move further apart in frequency, means the two consecutive signal has get separated by some gaps, and this gap is known as the guard band. Okay, the function of guard band is to separate the two sampled signal. This is first one, this is second one. So the advantage of this thing, while filtering, there is no interference of another signal into that one. Okay, so here the filter characteristic recover the waveform from the sample data. So for filtering purpose it will be very easy. But in case of previous case, if we apply the practical filter, then some amount of another signals will get mixed together, or in the resultant signal will appear, and that is caused noise in the resultant signal. Okay, so for practical purpose, filtering purpose, we need the signal fs greater than twice fm. Okay, so here hence easier to perform the filtering operations. Typically low pass filter might be used to separate the baseband spectrum from those at higher frequencies. And now the third case, whereas if fs is less than twice 2 into fm. Okay, 2 into fm, this replicate will overlap. This replicates, the signal will overlap. As a result, the information loss will be there. This phenomena is known as the aliasing occur, causes undersampling. Okay, so when sampling frequency is less than twice fm, means it does not follow the sampling criteria or Nyquist criteria, then in that case the two signals, this is first one and this is second one, get overlap like this, and this overlap is known as the aliasing. The overlap is known as the aliasing, or this error is known as the aliasing effect, or we can say it is a fold over error, and this is caused due to the undersampling. And the condition for undersampling is fs less than 2fm, fs less than 2fm. While previous case, this is known as oversampling case. Okay, that is fs greater than 2fm. Okay, so note that to avoid aliasing, the Nyquist criteria fs greater than 2fm must be satisfied. Fs greater than 2fm must be satisfied. As in previous case, there is no overlapping. So hence, to avoid the aliasing or the overlapping, the sampling frequency fs should be greater than 2fm. This is an important phenomena of these things. Okay, so this is the ideal sampling, or we can known as the impulse sampling. Okay, so here we will stop here. In next session we will start the practical sampling. Thank you.